After studying this module, you shall be able to know about multiple regression models and assumptions governing it. Learn to estimate partial regression coefficients. Identify whether the model is good, fit or not using measures such as standard error, coefficient of multiple determination and adjusted coefficient of determination. Evaluate a T and F value to conduct hypothesis testing for individual regression coefficients and for significance of the model as a whole. So far, we are familiar with the concept of a simple regression model where we studied the influence of a single independent variable xi on a dependent variable yi through the following relation: yi is equal to beta naught plus beta 1 xi plus mu I. The influence on the dependent variable is divided into a systematic part beta naught plus beta I xi and a stochastic or random part mu I. The extent to which the independent variable influences the dependent variable or the goodness of fit is measured by the coefficient of determination r square. In case the value of r square is low, then one of the reasons could be that there may be additional explanatory variables influencing the dependent variable but have not been taken into consideration. Therefore, in certain cases, it becomes vital to use a multiple regression model with several predictors or independent variables. In this module, we will study the general form of a multiple linear regression model, the derivation of its coefficients using the OLS technique with its interpretation, the standard errors and the coefficient of multiple determination. We would further learn about the hypothesis testing for individual regression coefficients and the overall significance of multiple regression model. In fact, the simplest form of a multiple regression model is one with two explanatory variables yi is equal to beta naught plus beta 1 x1i plus beta 2 x2i plus mu I, where yi is the dependent variable, beta naught is the intercept term, beta 1 and beta 2 are the partial regression coefficients, x1 and x2 are the two explanatory variables, mu I is the error term. The study of multiple regression model is the extension of simple regression model and would be discussed in detail in this module. Multiple regression equation. General form. The general form of the multiple regression model in k explanatory variables is yi is equal to beta naught plus beta I x1i plus beta 2 x2i plus beta 3 x3i plus so on beta k xki plus mu I, where beta naught is the intercept term, x1, x2, x3, xk are the explanatory variables, subscript I stands for the ith observation, beta 1, beta 2 up to beta k are the partial or net slope coefficients that depict the change in y when their respective explanatory variable changes by 1 unit, keeping all other explanatory variables fixed. Like before, the influence on the dependent variable is divided into two parts. One of the systematic part explained through beta naught plus beta 1 x1i plus beta 2 x2i so on up to beta k xki, and the other is the random or stochastic part explained through the error term mu I. The simplest form of a linear multiple regression model is one with two explanatory variables and expressed as yi is equal to beta naught plus beta 1 x1i plus beta 2 x2I plus mu I. The multiple regression model is based on the same set of assumptions as specified for the simple classical linear regression model. However, there is an extra assumption of no multicollinearity which is added to the existing set of assumptions of the classical linear multiple regression model. The model is linear in parameters. The error term has 0 mean and follows a normal distribution E mu I equal to 0. The error terms are independent, that is, covariance between them is 0 or there is no autocorrelation COV mu I comma mu I is equal to 0 for all I not equal to j. The explanatory variables are fixed in repeated sampling. All error terms have equal covariance, that is, they are homoscedastic. Variance mu I is equal to sigma square. The number of observations is greater than the number of regression coefficients to be estimated. N is greater than k plus 1, where k is the number of explanatory variables. There is no multicollinearity between the explanatory variables, that is, explanatory variables do not share a perfect linear relationship. Under the set of assumptions, if we take expected value of both sides of a 3-variable regression model, we get E of yi given x1I comma x2I is equal to beta naught plus beta 1 x1I plus beta 2 x2I. The left hand side gives the most probable value of y given x1 and x2. This is a population regression function of y on x1 and x2. In the above equation, beta naught is the intercept term as usual. Beta 1 is the partial slope term which measures the change in y when x1 changes by 1 unit keeping x2 constant. Similarly, beta 2 measures the change in y when x2 changes by 1 unit keeping x1 constant. But as before, the population regression coefficients are difficult to measure as population data is seldom known. Therefore, we use a sample multiple regression model instead, given by yi is equal to b naught plus b1 x1I plus b2 x2I plus ei, where b naught is the sample intercept term, b1 and b2 are sample partial slope coefficients, x1 and x2 are the two explanatory variables. Ei is the sample stochastic error term. Also, the sample regression equation of y on x1 and x2 is given by yi cap is equal to b naught plus b1 x1I plus b2 x2I. Therefore, yi is equal to yi cap plus ei. The observed value of yi is made up of the estimated value yi cap and the error term ei. OLS estimation of regression coefficients. In the ordinary least square method, we try to minimize the sum of the squares of the residuals. As we already know from equation 6, yi is equal to yi cap plus ei, that is, ei is equal to yi minus yi cap. Sigma ei square is equal to sigma yi minus yi cap whole square. Substituting the value of yi cap from equation 5, we get sigma ei square is equal to sigma yi minus b naught minus b1 x1I minus b2 x2I whole square. By differentiating the equation with respect to b naught, b1 and b2, we get three normal equations 8, 9 and 10 as shown delta of sigma ei square upon delta b naught is equal to minus 2 sigma yi minus b naught minus b1 x1i minus b2 x2i equal to 0. Sigma yi is equal to nb naught plus b1 sigma x1i plus b2 x2i. Delta sigma ei squared upon delta b1 is equal to minus 2 sigma x1i multiplied by yi minus b naught minus b1 into x1i minus b2 into x2i is equal to 0. Sigma x1i yi is equal to b naught sigma x1i plus b1 sigma x1i square plus b2 sigma x1i x2i. Delta of ei square upon delta b2 is equal to minus 2 sigma x2i multiplied by yi minus b naught minus b1 x1i minus b2 x2i equal to 0. Sigma x2i yi is equal to b naught sigma x2i plus b1 sigma x1i sigma x2i is equal to b2 sigma x2i whole square. Dividing equation 8 by n, sigma yi upon n is equal to b naught plus b1 sigma i1 upon n plus b2 sigma 2i upon n. Y bar is equal to b naught plus b1 x1 bar plus b2 x2 bar. B naught is equal to y bar minus b1 x1 bar minus b2 x2 bar. Taking deviations from respective means, that is yi is equal to yi minus y bar, x1i is equal to x1i minus x1 bar, x2i is equal to x2i minus x2 bar, and solving 8, 9, 10 equations simultaneously, we get values of regression coefficients as b1 is equal to sigma yi x1i multiplied by sigma x2i square minus sigma yi x2i multiplied by sigma x1i x2i whole upon sigma x1i square into sigma x2i square minus sigma x1i x2i square. B2 is equal to sigma yi x2i into sigma x1i square minus sigma yi x2i into sigma x1i x2i upon sigma x1i square into sigma x2i square minus sigma x1i x2i whole square. As the number of explanatory variables increase, calculation of regression coefficients become more and more complex. However, there are softwares available to calculate them with ease. Goodness of fit and hypothesis testing. Measures of goodness of fit. Once the multiple regression equation has been determined, the next step is to find out whether it is a good fit or not. Like previously, we have two indicators available to satisfactorily conclude about the goodness measure. These are 1. Standard error of estimate S.E.E. It measures the extent of dispersion of the observed values of dependent variable yi when its estimated values in the regression. The smaller is the standard error of estimate, the better is the fit. S.E.E. is equal to square root of sigma yi minus yi cap whole square upon n minus k plus 1. N minus k plus 1 in the denominator is the degrees of freedom for a regression line with k explanatory variables and therefore k plus 1 regression coefficients to be estimated. The numerator is the squared residuals which are to be minimized when the OLS method S.E.E. is equal to under the root sigma EI square upon n minus k minus 1. In a 3-variable regression, with one dependent and 2 independent variables, the degrees of freedom in the denominator would be n minus 3, as we are estimating 3 regression coefficients B0, B1, B2. Then multiple coefficient of determination R square. The multiple coefficient of determination carries the same interpretation as in case of a simple 2-variable regression model. It measures the extent of the variation in the dependent variable that is explained by all the explanatory variables together. The higher the value of R square, the better is the fit or the explanatory power of the model. To determine R square, let us start with a 3-variable regression model. Yi is equal to B0 plus B1 x1i plus B2 x2i plus Ei, same as equation 4. Also, Yi is equal to Yi cap plus Ei from equation 6. We know Y bar is equal to B0 plus B1 x1 bar plus B2 x2 bar, same as equation 11. Subtracting equation 11 from equation 4, Yi minus Y bar is equal to B1 into x1i minus x1 bar plus B2 into x2i minus x2 bar plus Ei. Or Yi is equal to B1 x1i plus B2 x2i plus Ei. Also, Yi is equal to Yi cap plus Ei. Therefore, Yi cap is equal to B1 x1i plus B2 x2i. Summing and squaring both sides of the equation 18, we get sigma Yi square is equal to sigma Yi cap plus Ei square. Sigma Yi square is equal to sigma Yi cap square plus sigma Ei square plus 2 sigma Ei Yi cap. Since last term of the above equation is 0, as the error term is unrelated to predicted Y values. Therefore, sigma Yi square is equal to sigma Yi cap square plus sigma Ei square. Sigma Yi square is equal to sigma Yi minus Y bar whole square, total sum of squares. Sigma Yi cap square is equal to sigma Yi cap minus Y bar whole square, explained sum of squares ESS. Sigma Ei square is equal to sigma Yi minus Y cap whole square, residual sum of squares RSS. Using terminology, equation 20 can be written as TSS is equal to ESS plus RSS. Dividing by TSS throughout, 1 is equal to ESS upon TSS plus RSS upon TSS. By definition, ESS upon TSS is equal to R square. R square is equal to 1 minus RSS upon TSS, which implies R square is equal to sigma Yi cap square upon sigma Yi square. R square is equal to 1 minus sigma Ei square upon sigma Yi square. Using equations 20 and substituting the values of sigma Ei square as sigma Yi minus B1 x1i minus B2 x2i whole square from equation 19 in it. Sigma yi square is equal to sigma yi cap square plus sigma ei into yi minus b1 x1i minus b2 x2i. Considering the last term of the term of equation, sigma ei square is equal to sigma ei into yi minus b1 x1i minus b2 x2i. This is equal to sigma ei yi minus b1 sigma ei x1i minus b2 sigma ei x2i. We know, as per the assumptions of classical linear regression model, the error term is unrelated to the explanatory variables. Therefore, sigma ei x1i is equal to sigma ei x2i is equal to 0. Sigma ei square is equal to sigma ei yi. Substituting value of ei from equation 18 in equation 19. Sigma ei square is equal to sigma yi into yi minus b1 x1i minus b2 x2i. Sigma ei square is equal to sigma yi square minus b1 sigma y1 x1i minus b2 sigma yi x2i. Substituting the values of sigma ei square from equation 27 in equation 24. Sigma yi square is equal to sigma yi cap square plus sigma yi square minus b1 sigma yi x1i minus b2 sigma yi x2i. Cancelling sigma yi square from both sides, we get sigma yi cap square is equal to b1 sigma yi x1i plus b2 sigma yi x2i. Substituting in equation 22, therefore, r square is equal to b1 sigma yi x1i plus b2 sigma yi x2i upon sigma yi square. The value of r square, as in case of simple regression model, lies between 0 and 1. If r square is 0, it implies that the explanatory power of the model is nil, that is, no variation in y is explained by our chosen independent variables. But if r square is equal to 1, it implies 100% of variation in y is together explained by all our independent variables, leaving none as unexplained. Hence, concluding that our model is an excellent fit. Adjusted coefficient of determination r bar square. We can always argue that as the number of explanatory variables increase in our regression equation, the value of r square goes up even when the explanatory variables chosen are nonsensical. This is because r square is equal to 1 minus sigma ei square upon sigma yi square from equation 23. As the number of regressors x variables increase, sigma ei square is equal to sigma yi minus yi cap whole square reduces as yi cap increases. Addition of a new variable increases yi cap and reduces ei. At least it does not increase sigma ei square. Therefore, if sigma ei square decreases, 1 minus sigma ei square upon sigma yi square or r square would increase as the denominator. Sigma yi square is equal to sigma yi minus y bar whole square would not change as it is independent of the number of explanatory variables. Therefore, there is always an incentive to increase the number of explanatory variables and get a higher R-square value, as a higher R-square is indicative of greater explanatory power of the model. It hence becomes imperative to look for a different and better measure of goodness of fit. This new measure is the adjusted coefficient of determination R bar square, a measure that is adjusted for the degrees of freedom for the number of explanatory variables chosen in the model. R bar square is equal to 1 minus sigma EI square upon n minus k minus 1 whole upon sigma yi square upon n minus 1. Kindly note the numerator is adjusted for the degrees of freedom of the RSS sigma EI square. N is reduced by k plus 1 here, as k plus 1 is the total number of regression coefficients to be estimated in the regression model with k explanatory variables. Likewise, the denominator is adjusted for the degrees of freedom of the TSS sigma yi square is equal to sigma yi minus y bar whole square, where 1 degree of freedom is lost when trying to estimate y bar. It is visible that as the number of explanatory variables increases, k in the model sigma ei square decreases to increase r square. But when we use adjusted r square, an additional degree of freedom is lost while trying to estimate an extra regression coefficient. With this loss of the increase in sigma ei square is countered through decrease in degrees of freedom, resulting in an increase of the value of sigma ei square upon n minus k minus 1 whole upon sigma yi square n minus 1. And therefore, reduction of r bar square is equal to 1 minus RSS upon n minus k minus 1 whole upon TSS upon n minus 1, which implies r bar square is equal to 1 minus RSS into n minus 1 upon n minus k minus 1 into TSS. A new term n minus 1 upon n minus k minus 1 is multiplied to RSS upon TSS. Mathematically, n minus 1 will always be greater than n minus k minus 1 for k is greater than 0. This implies that r bar square would always be less than r square. Substituting the value of r square from equation 21a in equation 31, we can draw a relationship between r square and r bar square. R bar square is equal to 1 minus r square into n minus 1 upon n minus k minus 1. Testing of hypothesis. Hypothesis testing for individual partial regression coefficients. Each individual regression coefficient is tested to determine whether it is significant, significantly different from 0 or not at a particular level of significance alpha, usually taken to be 5%. The steps followed are exactly similar to those followed in case of a simple regression model. For instance, if we need to test whether the coefficient b1 of the explanatory variable x1 is significant or not, we follow the following procedure. Set up a hypothesis H0, beta 1 equal to 0. Null hypothesis states that the variable x1 is insignificant. H1, beta 1 is not equal to 0. Alternate hypothesis states that it is significantly different from 0. State level of significance alpha is equal to 5% or 0.05. Determine the t statistic t is equal to sample statistic minus population parameter upon standard error of relevant coefficient. In this case, T beta 1 is equal to B1 minus beta 1 upon S into EB1. T beta 1 is equal to B1 upon S into EB1. As hypothesized, value of beta 1 is equal to 0. Decision making. The value of T statistic in step 3 is compared with the relevant T table value for the relevant level of significance and degrees of freedom n minus k minus 1, where k is the number of explanatory variables. If calculated value of T is greater than table value, that is T is greater than plus minus table value in case of two-tailed test, we reject the null hypothesis and conclude that the variable is insignificant. Likewise, the significance of the intercept term and all other partial slope coefficients can be determined. Testing the overall significance of the model. To test the overall significance of the model, we use the ANOVA analysis of variance approach. This approach tests the null hypothesis whether all partial slope coefficients are simultaneously equal to 0 as against the alternate hypothesis that they are not simultaneously 0. H naught, beta 1 equal to beta 2 equal to beta 3 all equal to beta k equal to 0. H1, beta 1 not equal to beta 2 not equal to beta 3 and so on not equal to beta k not equal to 0. If the null hypothesis is rejected, then the model is said to be overall significant. To test the above hypothesis, an ANOVA table needs to be constructed as to evaluate a F statistic. ANOVA for multiple regression. Source variation, sum squares, degrees of freedom, mean sum of squares. 1. Due to regression, ESS sigma yi cap square is equal to B1 sigma yi x1i plus B2 sigma yi x2i. Degrees of freedom is k and sum of squares is sigma yi square upon k. 2. Due to residuals, RSS sigma ei square n minus k minus 1 degrees of freedom and sigma ei square n minus k minus 1. Total variation is equal to TSS yi square n minus 1 degrees of freedom. F is equal to mean sum of squares of regression upon mean sum of squares of residuals, which is equal to sigma yi cap square upon k whole upon sigma ei square upon n minus k minus 1. Under the assumptions of normal distribution of error term, the F statistic calculated above follows a F distribution with k degrees of freedom in the numerator and n minus k minus 1 degrees of freedom in the denominator. Note that k as usual stands for the number of explanatory variables in the model. There are a 3-variable regression model, 1 dependent and 2 independent variables. The above statistic would follow a F distribution with 2, n minus 3 degrees of freedom in the numerator and denominator respectively. Once the F value is calculated, it is compared with the critical table value for relevant level of significance and degrees of freedom in the numerator and denominator. If F calculated is greater than F table, then we reject the null hypothesis and conclude that the model is overall significant. The simplest form of multiple regression model is the one with 3 variables, 1 dependent and 2 independent. The multiple regression model is the extension of the simple two-variable regression model. However, we have partial regression coefficients and partial correlation coefficients instead of regression coefficients and correlation coefficient. Goodness of fit is measured by the standard error of estimate, coefficient of multiple determination and adjusted coefficient of determination. The adjusted coefficient of determination is a better measure as it is adjusted for degrees of freedom. Testing of individual partial regression coefficients is done in the same way using a t-test. For the overall significance of the model, an ANOVA table is used to arrive at a f value.